Lesson 3 is coordinate proofs with slope. So in 3.1, we're going to be using parallel lines to prove objects are what we hope they are, and then in 3.2, we'll be using perpendicular lines. So just a quick little review, parallel lines, and we use like this symbol to, it's like shorthand for parallel. Parallel lines have the same slope, and we use M as our letter to represent slope. So parallel lines, same slope. And then perpendicular lines, what we'll be using in 3.2 is opposite, reciprocal slope. So opposite, reciprocal, which means like opposite in terms of like positive versus negative, and reciprocal is like a fraction flipped upside down. So like if my original slope was 3, then the perpendicular slope would be -1/3, the opposite reciprocal of 3. Okay, so 3.1, given that quadrilateral ABCD has vertices at A, 1, 4, which is right here, B, 4, 8, which is right here, C, 0, -5 right here, and then D, -3, -9 right here. We want to prove that quadrilateral ABCD is a parallelogram. And parallelogram is a quadrilateral, so something that has 4 sides, but there's 2 pairs of parallel sides. So that means that both like opposite sides are parallel. So parallelogram is 2 pairs of parallel sides. So on like this object, the one in the graph, it would mean that like this side and this side, like the 2 greenish sides are parallel, and then the 2 reddish sides are parallel to each other as well. So that would be like the 2 pairs of parallel sides. Okay, so in order to do this, we're going to have to find like the slope of all those different sides and kind of put them into our proof. So before we get started with the proof, I just want to kind of review the slope formula, which is m equals y1 minus y2 over x1 minus x2. Y1 and x1 are from one point, and then y2 and x2 are from another point. Okay, so we always start our proofs by just restating what is given to us. So that's this section up here. Given that quadrilateral ABCD has vertices at those 4 points, we'll just pretty much copy that exact statement down into our first statement on our proof. And then the reason is that it is given. And that's how always like our 2-column proofs start off, is just stating what's given to us. And then now we already talked about how like we're going to need to find the slope of these lines to prove that they're parallel, to see if we have 2 pairs of parallel sides. So that's what we'll do for step 2, is we'll start to find the slopes of each different like side of this quadrilateral. So it doesn't really matter where you start. I think I'm going to start with AB, which is like this side up here. And honestly, if you would prefer to just count rise over run, you can. I'm going to do that in the example for 3.2, so I'm going to use the slope formula for this example. So I'm going to say, I'm just going to shorten slope with m. So the slope of segment AB is equal to, so it's going to be the slope formula. For this one, I'll write it down. For the rest of them, I probably won't. So y1 minus y2 over x1 minus x2. Maybe I will just kind of copy it down so it doesn't take up that much space. You don't have to write it down each time though. Okay, so A and B, or segment AB, has like vertices at point A, so 1, 4, and then point B, so 4, 8. So it really doesn't matter which one you make your point 1 and point 2. I'm going to make B my point 1 since it has like bigger numbers, and then point A will be my point number 2. Okay, so that means that this is my like x1, y1, x2, y2. So 8 will go in for y1, and then 4 will go in for x1, and then 4 will go in for y2, and 1 will go in for x2. So 8 for y1 minus 4 for y2, and then over 4 for x1 minus 1 for x2, and then from there we can subtract. So 8 minus 4, 4 over 4 minus 1, 3. So we found our slope for side AB. I'm going to go ahead and find the slope of the one that we're hoping that's parallel to it. So that would be CD down here. So the slope of segment CD is equal to, and I'm just going to copy down the slope formula. You don't have to rewrite it if you don't want to, but just so we can kind of see like what is getting substituted in where. So this segment has vertices at C and D, so I'm going to change my points over to those. This one has a ton of negatives, so it really doesn't matter like which one is our point 1 and point 2. I feel like it's equally not that great, but I'm going to make C point 1 and D point 2, so those will be my x1, y1, and then x2, y2. So let's see, y1 will be -5, and then y2 will be -9, x1 will be 0, and then x2 will be -3. So y1, that was -5, minus y2, so it's minus -9. It has a double negative. And then x1, which is 0, and then minus -3, so another double negative. Anytime you have minus a negative or a double negative, it turns to a plus. So this turns like into a plus right here. So like -5 plus 9 would be 4. And then same thing in the denominator, -0 minus -3, the double negative turns into a plus. So it'd be like 0 plus 3, so 3. So far we checked the two, like one pair of segments or sides that we thought would be parallel, and they are. So far so good, because we got two like segments that each had a slope of 4/3. So we're on the right track. We just need to prove that the other pair of like kind of opposite sides are also parallel. So it's going to be AD and BC. So it doesn't matter which one we do first. I'm going to do AD first. Looks like I gotta shrink this way down because I wrote way too big. Okay, so next we'll find the slope of, let's see, AD. So that means that my endpoints are going to be point A and point D. I think I'm just going to like leave D labeled as point 2 to save a little bit of time. So point A will now become my point 1. So this would be my x1, y1, and then the points from point D will be my x2 and y2. So x1 is going to be 1, and then y1 is going to be 4. So if we start putting each thing in, y1 is 4, and then minus y2 is -9. So minus -9 over x1 is 1, and then minus x2 is -3, so minus -3. We have some double negatives again, so those double negatives will turn into a plus. So 4 minus -9, that double negative will turn into 4 plus 9, so that's 13. And then in the denominator, 1 minus -3 will turn into 1 plus 3, so that would be a 4. So 13 over 4 is my slope of segment AD. Let me shrink this down one more time. And then we'll find the slope of that final side, so it should be CB or BC. Okay. So for the final side, the slope of side BC, same slope formula. I'm just going to copy it down. You really only need it one time if you're comfortable with that. And then since my side now is BC, that changes my vertices to B and C. So those are going to be the points that I use for the slope formula. So and see B and C right here. I'm going to make my B my point 1 and then C my point 2. So this will be x1, y1, this will be x2, y2. And if you're ever having a hard time with like the slope formula at all, you can also count rise over run from the graph. It's just I noticed some of the like questions like in the checkpoints and stuff have all the slope formula stuff worked out. So I wanted to at least give you one example there. So I accidentally put y1 instead of y2 on point C, sorry. So point C was like the point number 2, so x2 is going to be 0 and y2 is going to be -5, and then point B is my like point 1. So y1 is 8, and then y2 is -5, and then x1 is 4, and x2 is 0. So we'll plug everything in. So y1, that was 8. y2 is -5, so minus -5. x1 is 4, and then minus x2 is 0. And then in the numerator, we have that double negative, so 8 minus -5 turns into 8 plus 5, so that's 13, and then 4 minus 0 is 4. So we ended up with 13 over 4. So if you notice, like the first two were those red sides that we were trying to pair up and make sure those were parallel. And then the last two, those were those like kind of greenish sides that we were trying to show were parallel. And we did. Those both ended up having a slope of 13 over 4. So now we just kind of got to like find a way to like present that in more of like a proof like manner. For our like reason for number 2, we just use the slope formula, so we can use that as our reason. That's exactly what we did. We used the slope formula. So reason for number 2, slope formula. Took a ton of work, but at least the reason is pretty straightforward. And then now for statement number 3, we can go ahead and say that like those pairs of segments are actually parallel to each other, you know, like the ones that both had 4/3 and the ones that both had 3/14 or 13/4 as their slopes. So it's going to be AB is parallel to CD because they both had 4/3 as their slope. And the way that we write that is segment AB. And then in the like proofs, we just use like 2 vertical lines to represent parallel. Sometimes you use slanted for like shorthand, but in proofs we use like the 2 vertical lines. That means parallel. But segment AB is parallel to segment CD. So they both had slopes of 4/3. If lines both have the same slope, that means they're parallel to each other. And then the other pair of segments that had the same slope, that was AD and BC. So we would say segment AD is parallel to segment BC. And then for our reasoning, it can be kind of what we just talked about, how if lines have the same slope, that means they're parallel. So we can say lines with an equal slope. So lines with equal slopes are parallel. So lines with equal slopes are parallel. And then think about what we kind of set out to prove at the very beginning. So up at the top, we were trying to prove that, I'll zoom out in case anybody's still writing. We're trying to prove that quadrilateral ABCD was a parallelogram, and parallelograms have 2 pairs of parallel sides. And in 3, we just proved that we not only have 1 pair of parallel sides, but a second pair of parallel sides, which that's all we need to do to prove that the quadrilateral is a parallelogram. So that means we just need to wrap up our proof there. So we would say for 4 quadrilateral, I'm just going to shorten it to quad. So quadrilateral A, B, C, D is a parallelogram. And then for our reason, we can say that both sets of opposite sides were parallel. So for 4, quadrilateral ABCD is a parallelogram. And then for the reason, both sets of opposite sides are parallel. Okay, so to just kind of look back at the proof as a whole, for statement number one and reason number one, it was just the information that was given to us. We set out and we wanted to kind of prove that the opposite sides had parallel or had the same slopes to show that they were parallel to each other. So we showed that the two red sides, they both have a slope of 4/3, so those are parallel. The two green sides, those both had a slope of 13/4, so those were parallel. And then we were able to say that they're parallel because they have the same slopes, and that's kind of just the definition of parallel. And then once we were able to say that those two opposite sides, two pairs of opposite sides were parallel, that's enough to say that it is a the quadrilateral is a parallelogram because both sets of opposite sides are parallel. Okay, so moving down to 3.2. This is using perpendicular lines to prove objects are what we hope they are. So in this one, we're given another quadrilateral. This one has vertices at the point A, which is -3, -8, B, which is -8, -4, C, which is 0, 6, and D, which is 2, 5. And on this one, we want to prove that quadrilateral ABCD is a rectangle. So same kind of start, we're just taking whatever is given to us, like the exact statement, putting that as our first statement in here. So quadrilateral ABCD has vertices at those 4 points, and the reason is that it's given to us. Like I said, that's how we'll start pretty much every single 2-column proof that we do. And then this proof does end up being a little bit longer, so I'm going to take a little bit different approach, just we have kind of also a different version of an example of finding the slope. So in order to prove that this is a rectangle, we really just need 4 right angles. So we need a right angle right here, right here, right here, right here. And the types of lines that intersect at a right angle, they are perpendicular lines. So if we can prove that all of these lines are perpendicular, then we can confirm that the quadrilateral is a rectangle. In order to prove that the slopes are perpendicular, their slopes need to be opposite reciprocals. The way that we'll write it in the proof, though, is that the product of the slope is -1. That was one of the things that was kind of introduced in that perpendicular section. So I'm going to add perpendicular. That's the symbol for perpendicular. Slopes are opposite reciprocals, yes. Meaning 2 and -1/2. So opposite reciprocals, and the product of them equals -1. So for example, 2 times -1/2, if you were to multiply 2 times -1/2, that would equal -1. Or 3/4 times -4/3, if you were to multiply those two together, that product would also be -1. So that's how we would have to show it for this proof. Okay, so before we can set out to prove that the slopes products are -1, we have to figure out what the slopes are of all 4 sides of this object. So that's what we're gonna do. I'm gonna start with just AB, so this side right here. And I'm not gonna worry so much about the slope formula for this one. I'm just gonna count rise over run. So the slope of segment AB, remember that if you want, instead of using the slope formula, especially if you have the graph in front of you, you can use slope equals rise over run. It ends up being the same exact number, it's just a different way of viewing it. So rise is vertical change, how far you go up or down, and run is horizontal. You can still use the slope formula for this problem if you feel more comfortable with it. I just wanted to do it a little bit differently this way. Okay, so from B to A, the rise is I have to go down 1, 2, 3, 4. So that would be a -4 since I'm going down 4. And then the run, I'm going over 1, 2, 3, 4, 5. So if it's rise over run, the rise is the vertical change, that's the green -4 because we went down 4, and then the run is the horizontal change, we went right 5, so it'd be +5. So the slope would be -4/5 for that first slope. And then for the second one, I'm going to find BC next. It really doesn't matter the order that you go in, but I'm going to find BC next. I'm going to keep the original slope on there, but between B and C, the rise, I would have to go up a lot, I guess. So it looks like I'm going up 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know if I counted that right now. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so we started at like, would be the easier way to do it. We started at -4 and we went up to 6. So that's up 10. So from here up to here, we went up 10. I think I am going to take away the old slopes just because I feel like it makes it look like it's all part of one big line. So the rise was 10, and then the run is we're going from B to C, so we're going over 1, 2, 3, 4, 5, 6, 7, 8. So the run is 8. So for the slope of segment BC, same thing, rise over run. So the rise was 10, the run was 8. If you have a fraction and you can reduce it, you should. So like 10 and 8 are both divisible by 2. So if I reduce by dividing both by 2, that would turn into 5/4. So it looks like we're on the right track because those are opposite reciprocals. We'll like eventually prove that they have like the same, or not the same, but they have a product of -1, but it looks like so far so good. Okay, so the next one I'm going to find is CD. So from C to D, we'll find rise over run. I'm going to erase the old ones just so it doesn't look like one like big section. You can go like either direction you want. You can go like out this way and then down, or you can go this way and then over. It ends up being the same. If you like doing rise first, we have to like go kind of inside. So I'm going down 1, 2, 3, 4. So that'd be a -4. And then I'm going over 1, 2, 3, 4, 5 to the right. So my rise would be -4. My run would be 5. So the slope of, I'm going to draw this in the next line. The slope of segment CD is equal to rise, which is -4, over run, which was +5. And then the last one we need to find now is just AD. So the slope of segment AD. So between A and D, we're finding like this side right here. So if I count my rise, I'm going from -8 like down or up to 2 up here. So it should be 10 units up. And then I'm going like to the right 8 units from -3 up to 5. And you can always count them, or you can do it by like checking the numbers and seeing the change. So we're going up 10 and then to the right 8. So the rise is 10. The run is 8, and then same thing, we can reduce this, so we can divide 10 and 8 both by 2. So 10 divided by 2 is 5, 8 divided by 2 is 4. Okay, and then for our reason for step 2, even though we did like a different version of the slope formula here, we still just use the slope formula, which is kind of a different version with the rise over run. So for my reason, it'll be slope formula. And then for number 3, we need to start building towards being able to like prove that the lines are perpendicular. So even if you like are looking at these slopes now and you're like, those are all opposite reciprocals of each other, so like they must be perpendicular, we have to like really be able to prove it. So we do that by showing that their products are -1. So we need to kind of like pair up like each of the like intersecting sides. So we'll start with like it doesn't matter where we start, but we'll start with like this corner right here. So that would be the intersection of like AB and BC. So we'll say that the product of those two slopes is -1. So we'll say the slope of AB and then times the slope of BC equals -1. And it's true, because if we take AB, that's -4/5, and then we were to multiply it by the slope of BC, which is 5/4. If you take a number and multiply by its reciprocal, it's 1, and then we're multiplying a positive times a negative. I'm going to go ahead and just write that one out. The first time I will end up erasing it though, so if you need it, you can pause, but the slope of AB is -4/5, and then times the slope of BC, which is 5/4. Even if we just multiply straight across here, like in the numerator, it would be -4 times 5, which is -20. And then in the denominator, it would be 5 times 4, which is that +20. And then -20 divided by +20 would be -1. So we get that -1 product. That'll always happen when you multiply a number by its opposite reciprocal. You'll get a product of -1. Okay, so I'm going to erase this just for space. We just need to show that for all 4 corners, meaning that like all 4 corners are the result of like inner or perpendicular lines intersecting. So we did that first corner. I'm going to leave that just kind of like color code it. So that first line was our pink corner, and then the like second corner we'll do up here. So that's the intersection of BC and CD. So we'll say the slope of BC times the slope of CD is -1. And then same thing there, because those are opposite reciprocals. So BC was 5/4 and then CD was -4/5. So opposite reciprocals, if we were to multiply them together, their product would be -1. So that's that second corner, and we just need to show all 4. So the third corner now, we'll do this one like around angle D. So that'll be the intersection of CD and AD. So we'll say the slope of CD times the slope of AD, that product is -1 as well. Looking at both of those slopes, the slope of CD is -4/5, and then the slope of AD is 5/4, so opposite reciprocals. So we have that, oops, sorry, I erased too much. We had that that third corner now, and now I just need to find the fourth corner at like angle A, which that's the intersection of AD and AB. So we'll say the slope of segment AD and then times the slope of segment AB. So if we take those two slopes and multiply them together, AD was 5/4 was its slope, and then the slope from segment AB, that was -4/5. So a number times its opposite reciprocal, it's going to give us a product of -1. Okay, sorry, I know this is tedious. I think I just got my first hand cramp in a while. But that's why I tried to make like finding the slope a little bit less bad with the rise over run. But that part was kind of a doozy. Okay, so we have shown that like all 4 segments are perpendicular because their slopes have a product of -1. So all we did for like 3 though is we're building up to like being able to say that they're perpendicular. All we did for 3 is multiply those, so we're not going to get crazy with the reason. We're just going to say multiply. You can say multiply or multiplication. All we did was multiply the slopes, and those slopes or those products happen to have like an answer of -1. So all we did was multiply the slopes together and just find that their product was -1, but that helps us be able to like prove that the segments are perpendicular. So for 4 now, we can go ahead and pair each one up and say that they are perpendicular. They'll stay paired up just like these ones are. So the first one will be AB is perpendicular to BC. So AB is perpendicular to BC because they had that product of -1. And then next we'll do BC is perpendicular to CD. So segment BC is perpendicular to CD because they had that product of -1. So that's the first pair. That's the second pair. The third pair was segment CD is perpendicular to segment AD. So CD is perpendicular to AD, again, because they had that product of -1 when we multiplied their slopes. And then the last pair is AD and AB. So segment AD is perpendicular to segment AB. Same thing, because they had that product of -1 between their slopes. And like our reason for this is just exactly what I've been kind of saying after like each line. It's if the product of the slopes of the lines are -1, they're perpendicular. So if, this will be a little bit longer, sorry, if the product of their slopes is -1, the lines are perpendicular. So if the product of their slopes is -1, the lines are perpendicular. And then in order to be able to like ultimately show that, you know, this is a rectangle, they have to, like, we have to prove that the four corners of the rectangle or the four like interior angles are right angles, because that's what makes it a rectangle versus a parallelogram. Is a rectangle would have four right angles. And that's what happens when perpendicular lines intersect. They create right angles. So like all these kind of corners that we were checking on when we were like kind of showing the combination of the two sides, we were basically checking to see if those corners were right angles, and they are, because these sides are all perpendicular to each other. So for 5, we're just going to go ahead and say that they are right angles. So for angle A, angle B, angle C, and angle D are right angles. And then our reason is that, you know, we already proved that they're perpendicular lines that are intersecting to form those. So perpendicular lines intersect to form right angles. So perpendicular lines intersect to form right angles. Okay, and then for 6 now, we've shown that all 4 angles are right angles. That's what we needed to prove, to show that it was a rectangle, so we can close out the proof there. So to close it, we want our like finishing statement to match what we're trying to prove. So like we're trying to prove that quadrilateral ABCD is a rectangle. So we can just copy that like exactly as is for our final statement in our proof. So quadrilateral, I'm just going to shorten it to quad, but quadrilateral A, B, C, D is a rectangle. And then for our reason, think about like what we just said right previous to this, because a lot of times our reason is like based on the previous statement. So our previous statement was that there was those 4 right angles. Our reason is going to be if a quadrilateral has 4 right angles, then it's a rectangle. So if a quadrilateral, shortened to quad, if a quadrilateral has 4 right angles, I'm going to shorten angles to like the angle symbol. So if a quadrilateral has 4 right angles, then it's a rectangle. Okay, so zooming out, looking at this one as a whole, I apologize. I don't like to do this much writing for proof, so I'm sure you guys feel like you're in the same boat. But we had a quadrilateral, something that had 4 sides, like is what we were given, and we wanted to prove that it was a rectangle. So in order to do that, we had to prove that all 4 of those interior angles were right angles. In order to do that, we had to prove that the lines intersecting were perpendicular to each other. So that's what we did. We started with the slope, showed that they were perpendicular, then we're able to determine that we had right angles, then we could say it was a rectangle.